Hello, this is Nathan Smith. I'm preparing this video for my students in managerial economics in Visalia and North Fresno. So this is part 3, chapter 7, production, theory, and estimation. Okay, so we start with inputs, because sometimes these are called factors of production. The basic things that you input into the production process. We categorize them as labor, capital, and land. Those are the most fundamental. Now, for some processes, there are also intermediate goods. Like if you're making orange juice, you need oranges, for example. If you're making bread, you need flour. But then the flour is made by somebody else, so if you trace it all the way back to the sources, then it's labor, capital, and land are kind of fundamental. Anyway, just about any business needs those three, and some need some other intermediate inputs as well. Now, we'll make a distinction between fixed and variable inputs, and what this means is that fixed inputs, is that in the short run you probably can't vary them very much. So if you have a certain amount of machinery installed, or if you have a structure, you're kind of stuck with that. It's not going to be very easy to get more quickly. It's not going to be very easy to liquidate what you have if it turns out that it's more than you really need or can use profitably. So those are considered fixed inputs. Variable inputs, typically we think of this as being labor. Labor, you figure, is a lot easier to lay off if you don't need it, or to hire if you do need it. Now, that's not always true. In some cases, it might be that you have certain capital equipment that would be fairly easy to buy or to sell, and certain kinds of labor might be very difficult to hire. But in any case, you can make the distinction between fixed and variable inputs. And so when we're looking at the short run, that means there's at least one input that's fixed. In the long run, all inputs are variable. So that's the distinction we make between the short run or the long run. We don't necessarily define what period that is, but you have different kinds of ways of analyzing the problem. Okay, so now we're going to imagine two inputs, and this is giving an example of a production function. So production function is, you can think of it as a mathematical function that links the inputs into the production process to the outputs that come out of the production process. So in this case, there's two inputs. It's run as a table, and so for one capital and one labor, you get 3 output. For 2 capital and 1 labor, you get 7 output, and so on for all the cells in the table. So more capital, more labor tend to produce more, although in this case they've made it so that at some point you're actually just wasting it, and it's even getting in the way. So this is a representation of the same data as before, only in the form of a kind of a, I guess you could say, a chart. And this is more sort of abstractly drawn, so now they just make it kind of lines that are mimicking the structure of it. You can see the different points. You see, including points that are on the bottom layer. So with F, point F represents a certain endowment of capital and labor. Then this line segment FE represents the quantity that will be produced with that combination of capital and labor. Okay. Now, when I talk about the quantity that can be produced with a certain amount of capital and labor, that would be the total product. But we're going to do something here where we say production function with one variable input. So I mentioned before that we distinguish fixed and variable inputs. At this point, we'll assume that we're looking at the short run, and capital is not variable. You don't have time to change that. So total product is Q, and we're going to call that a function of labor. The marginal product, so by now you should be familiar with total, average, and marginal of all sorts of things. We've talked about mainly so far revenue and cost. Well, now we'll talk about product. So now when you talked about average revenue and average cost, we were doing it over quantity. Now we'll talk about over labor. So over the one input that we're changing. So the marginal product of labor is the change in the total product divided by the change in labor. The average product of labor is total product divided by labor. So how much are you producing per worker? And then we've got an elasticity. And the elasticity turns out to be the marginal product divided by the average product. And you maybe see that if you imagine elasticity is always a percent change in one thing over a percent change in something else. So if you divided this by this, you'd end up with delta TP over TP, delta L over L. That's the percent change in total product divided by the percent change in labor. That gives you elasticity, output elasticity of labor. Okay, so this puts it all in a table, and so we're assuming a certain quantity of capital. I guess we're assuming 1 capital. So capital is 1, and at that level of capital, this tells you how much you can produce for these numbers of workers. That tells you the marginal product of labor, average product, and the output elasticity of labor. Percentage increase in output for a percentage increase in labor. Okay. So this is just plotting the total product curve that we just saw. This plots the marginal product of labor and the average product of labor. Note that the marginal product is plotted halfway between the successive units of labor used. So again, we ran into this little tricky issue before, which we've handled in various ways, where the marginal product is really defined over an interval. So that's why that's drawn that way. But now here we kind of distinguish. First, these are drawn a little bit smoothly, so we treat labor time as continuously divisible. So, maybe you can hire part-time workers, or you can ask workers to work overtime, so you're not constrained by units there. But so we distinguish stage 1 of production for labor. This is the rising proportion of average product. So this is where average product is rising. You're actually increasing your product per worker. Stage 2, you notice average product is falling, but marginal product is still positive. And then stage 3 is where marginal product is negative. So in this stage, you're getting economies of scale. You're actually, maybe you're dividing the tasks more. Workers are getting more efficient at some subtask. Here, to some extent, you're overcrowding the production process a bit, so that workers are maybe getting in each other's way a little bit, so they're less productive as you get more of them. Or maybe the most valuable tasks are already being done, so you have to move to less valuable tasks. So that's stage 2, and then stage 3, and you'd never really want to be out of here, because obviously you could just lay off these workers and you actually increase your product. And do production processes they never go out here, presumably, I think. Maybe they would if firms were stupid enough to hire that many workers. But anyway, in the abstract, we're thinking about all different situations. Okay, so marginal revenue product of labor. We talked about marginal product of labor, didn't we? I think so. Yeah, marginal product of labor. Now, marginal revenue product. This is where you multiply the marginal product of labor times marginal revenue. This tells you how much more revenue an extra worker generates. And you note that if marginal revenue is negative, marginal product might actually be positive. So I guess in principle they could both be negative, but I mean that's not ever going to happen in practice. You'd never be producing at that stage. But never mind. That's a long story. But marginal product of labor could be positive So the extra worker is producing more, but marginal revenue is negative. So he's just basically flooding the market and driving the price down, so he actually reduces your revenue. That would be one possible situation here. Marginal resource cost of labor. It's change in total cost divided by the change in labor. So how much does it cost you to hire an extra worker? And so you get your optimum when these two are equal. Again, whenever we're looking at this optimization, maximizing profits, and so on, we're usually setting up the marginal of something to the marginal of something else. In this case, it's the marginal revenue product of labor to the marginal resource cost of labor. Those should be equal, and at that point, you're choosing the optimal amount of labor. So here's an example. Units of labor, marginal product. You notice the marginal product is falling. So in this case, as you're hiring more labor, you have fewer and fewer useful things for them to do. This extra part-time worker here at the end, you don't really have anything useful for him to do, so zero marginal product. Now, marginal revenue, it's just if you produce an extra unit, whatever number of units of labor that would take. If you do produce and sell an extra unit, how much extra revenue do you get? It's always 10. So in this case, you can imagine a company which is not facing a downward sloping demand curve. It's facing a flat demand curve. It's operating in a perfectly competitive environment. However much it wants to make, it can sell at the market price, which is 10. So marginal revenue product is the multiple of these, and marginal revenue product is falling because even though marginal revenue is constant, marginal product is falling. So marginal revenue product starts at 40, gradually comes down. Marginal resource cost, meanwhile, is level. It's constant at 20. Okay, and so this just graphs that, and you see where they intersect each other, and that's your optimal use of labor, 3.5 units. Okay, so now, so far we've been looking at just one variable input because we're assuming that the capital is fixed, and so we're interested in, you can think of, we've been talking about the short run so far. Now maybe we're thinking about the long run, or at any rate there are two variable inputs, and we need to use a little bit different methods for that. In particular, we develop something called isoquants. So isoquants will be, well, you'll see them in a minute, but they're combinations of two inputs that can produce the same level of output. So probably labor and capital, for example, produce the same level of output. Firms only use combinations of two inputs that are in the economic region of production. You'll see what that means. It'll be pretty obvious once you see it. So each isoquant is negatively sloped. So here we draw isoquants in the table that we had before. I mean, we're interested in getting the same, when we see the same values. So 12, 12, 12, 12, 28, 28, 28, 28, 36, 36, 36, 36. And, I mean, you know, it's this odd situation. You don't have anything to do with this labor, so it's just basically wasting, you know, your human resource budget. In this case, you don't have anything to do with this capital, so it's just sitting down, occupying floor space. You're always going to want to, you're not going to want to operate up here, because capital is costly. Not going to want to operate here. Labor is costly. I mean, here you could reduce your capital and labor and keep the same amount of production. In fact, you could then reduce capital again. You're definitely not going to want to be up here. You'll always want to be in the part of the curve, not this actually, just this part, that's negatively sloped. And that's where you're facing a trade-off between labor and capital. If you want to produce the same amount and use less capital, you have to hire more labor. You have to replace that. So these are drawn in a little bit more abstract space. The numbers are taken away. It's the same, I believe it's the same numbers, but the curves are more clearly drawn. They may add in some points, I'm not sure exactly. But anyway, this is an example of isoquants, and you notice they do actually wrap around a little bit, so so there's only a certain part of them that has that negative slope, and you're definitely going to be want to be in that part of the slope. Okay, so this and identifies what's called the economic region of production. There's some limit, you know. There's within this region, you're not wasting any resources. You're making use of all your capital, all the capital and labor that you're using in the production process is actually increasing your marginal product. Okay, so within that range, then we can have a concept of something called the marginal rate of technical substitution. So technical substitution is a trade-off between production inputs. So trading off capital for labor, for example. So in this case, along the isoquant, it's the negative of the change in capital over the change in labor, or the ratio of the marginal products of capital and labor. That's the marginal rate of technical substitution. And the marginal rate of technical substitution will change along the isoquant. So at this particular point, then you see the marginal rate of technical substitution. You see the tangent line, the slope of the tangent line is shows you what the marginal rate of technical substitution is at this particular point, R. So yeah, the marginal rate of technical substitution at any point on isoquants is given by the absolute slope of the tangent line. And you notice it changes over the length of the slope. So up here at n, the slope would be much steeper. And the idea there is, well, okay, so at this point, you've got a lot of capital, you've got very little labor. You probably picked a lot of functions in which labor would be sort of relatively quite efficient, and capital can't do the job that well, but for some reason you've chosen to be up there. Maybe the reason you've chosen to be up there is because wages are really, really high. And in the same fashion, if you're down here, then the isoquant would be much more favorable to where you could, just a little bit of capital can do you a lot of good. I've heard about production processes in India where you've got 50 men doing work that 5 people could do if they just had wheelbarrows. Maybe labor is so cheap in India, or was, that that it's not worth buying the wheelbarrows. You'd rather just hire 50 people than spend that money on wheelbarrows. That certainly wouldn't happen in the U.S. In the U.S., you typically have not only wheelbarrows, but bulldozers and all kinds of fancy equipment because labor is expensive, so you often want to substitute capital. And if you imagine, you could have robot checkout clerks in the supermarket. Well, that might be possible if you worked really hard at it. It would probably be very expensive. It would only be worth it if labor costs were really high. So depending on the relative prices of labor and capital, you'll want to be at different places along this isoquant. These are a couple of special cases of production functions. So in this case, capital and labor are perfect inputs for each other. So you can either get a machine to do it or you can get a worker to do it. They do it equally well. It doesn't really matter what the mix is. This is a different case. This would be a case where, let's say, it only takes one worker to do it. They have to have a tool to do it. So they have to have some capital. They can't do it without the tool. But they only need the tool. And once they have the tool, there's nothing else you can really do to give them to make them more productive. That's just the limit on how productive they could be. Taxis might be like this. It might be, you say, well, to carry a passenger, you have to have one car and one driver. There's really no other choice. And if you give the driver 2 cars, that doesn't do him any good. And if you have 2 drivers and one of them doesn't have a car, that doesn't do any good. You have to have a perfect match. So perfectly complementary inputs in that case. Okay, so isocost lines. So we talked about isoquants. Now isocost lines. Isocost mean every point in this curve, or this line, every point of the line represents a bundle of inputs that costs exactly the same as every other point on the line. So it's kind of visible. The way to tell, you can take the endpoints, and if you assume there's a certain price, so the slope of the isocost line is the relative prices of the 2 goods, then as you move along here, If you're at this corner, you say you're spending all your money on capital. As you start buying more labor, you have to sacrifice capital, and if the prices are the same, which is often a reasonable assumption, the prices don't vary depending on how much you buy, then that will have the shape of a line. But you notice the slope will depend on the relative prices. So in this case, you can afford a lot of labor, not that much capital. In this case, you can afford more capital, not as much labor. In this case, wages are lower. This represents an ISO cost line for a rather low wages. The A, B star, A prime, B prime. That represents an ISO cost line with somewhat higher wages. But your budgets might have increased overall because you can afford more capital. Or maybe capital's cheaper. Maybe some combination of the two. If you compare AB and AB star, this represents a case where you have the same budget, or at least you're looking at the same ISO cost line, but labor's become cheaper. So if you move from AB to A prime, B prime, you're deciding to spend more. If you move from AB to A double prime, B double prime, you're deciding to spend less. So, what's the best way to produce goods? This is kind of similar to the consumer's problem. It's a problem of constrained maximization. We're going to look for the point where the ISO cost line is tangent to the ISO quant. This is what I already said. ISO cost lines represent all combinations of two inputs that a firm can purchase with the same total cost. So you've got some total cost, and then you've got wage times labor. This is the labor cost plus your capital cost, and there will be a lot of different choices of L and K that can satisfy this equation, and then we'll form the ISO cost line. Okay, so now we've got a series of ISO quants, and then we've got a bunch of ISO cost lines. And in this case, then as you move out, at each point you'll look for the place where the ISO quants are tangent to the ISO cost line. Now, this doesn't tell us which of these. So this is for quantity 8, this is for quantity 10, this is quantity 14. It doesn't tell us which of these we prefer. Typically, you'll actually have all these options. If you have fairly good access to finance, you'll have some scope to expand your production or not. And just this analysis will not tell you how to make that decision, whether to expand or not. But for any given scale, this will tell you the cost minimizing way of producing that quantity. So D represents the cost minimizing way of producing quantity of 8. E is the cost minimizing way of producing quantity of 10. F for producing quantity 14, etc. Given the relative prices of labor and capital that are represented by the ISO cost line. So we can imagine a situation in which the relative prices change. So, for example, let's suppose that you start at let's start at AB. So we start at AB, and at AB, then E represents the cost minimizing method of production. But now let's suppose labor falls in cost. Labor becomes twice as cheap. Well, if you want to incur the same cost that you did before, $100 worth of cost, then you can move out here to this line, and then you can actually produce at point N. And you notice you actually employ a little bit more capital in this case, but you employ a lot more labor because you expand production considerably. But you do it mainly by hiring more workers, since workers are suddenly so cheap. So that's moving from E to N, so that's one example. Or you might prefer to keep your quantity constant, continue producing 10, but you'll do it in a different way. So in that case, what we do is we draw a parallel ISO cost line. So instead of A, B star, we draw A star, B prime. So the isocost, we move to a different isocost line. And we're on the same isoquant in this case. So we move from E to R. We lay off a bunch of capital, make different plans, maybe we sell it off, whatever happens to it, but we stop using so much capital, stop renting it. Maybe if we were renting it, we just terminate the lease on some of that capital, and we also employ more workers, employ 3 more workers. And we end up producing the same amount, but notice our costs have fallen because we were spending 100, and now we're only spending 70. And we're producing the same amount. Okay. This is an example taken from the trucking industry, and so the trucking industry, they face a trade-off between they have 2 variable inputs here, driving time and gasoline costs. So they can either tell the truckers to spend more time on the road, or they can have them go faster, but if they go faster, they burn more gasoline. So if they're going to produce a certain amount of truck miles, whatever the unit, I think it's could be ton miles, but in any case, whatever that is, they're going to decide how to produce it. Well, they have a trade-off. They can produce it with less time but more gas, or more gas but less time. And this is an example of it. It's supposed to be an isoquant. And then you look at their isocost lines, because gasoline is always the same price, driving time is always the same price. And you notice that if there's a change, so from DE to GF, so at DE, well, actually, what's the example here? Yeah, you start at DE. So DE means you can buy, compared to FG, you can buy relatively little gasoline, but relatively a lot of driving time. So trucker's time is relatively cheap, gasoline is relatively expensive. So if you shift from DE to FG, what's happening there is you're now drivers have become more expensive, gasoline's become relatively cheaper. And so you respond to that by shifting from point B, where you're having the drivers go a little slower, you were using more of their time, to point C, where you tell them, okay, you can speed up now, you'll burn a little more gas, but that's okay, we want to get you to your destination faster and move you on to some other job. So that's an example. Okay, returns to scale. So this is the idea that if you increase both inputs, so now we're talking about increasing both inputs, in fact, by the same proportion. And maybe you think intuitively, well, if you're going to increase both inputs by the same proportion, then the output should increase by that same proportion as well. And sometimes that's true, but not always. You can have constant returns to scale, so that's if these two are equal. You can have increasing returns to scale. So that's if you increase labor and capital by the same amount, you actually produce more. Maybe it allows you to have more specialization in what your workers are doing, or more specialized capital. So you have the same total dollar value of capital, but maybe you have more sort of specialized machines that do particular jobs. So that could give you increasing returns to scale. Or you might have decreasing returns to scale. In this case, the most obvious reason might be that well, it could be that if you're building a really big plant, it's expensive to move everybody around within the plant, so that distribution issues, or it could be that the management just gets you're trying to manage such a large workforce, you need more layers of management, that ends up wasting a lot of time. Could be various reasons for that. This shows this is empirical work estimating returns to scale. So furniture, chemicals, printing, some of these have relatively high returns to scale. We move down. Some of these actually have negative. Well, sorry, have less than 1. So a few industries where you actually see decreasing returns to scale, according to this data. But more often, positive returns to scale. This is rather old, 1967. It'd be interesting to see what it would be now. But anyway, so this represents constant increasing and decreasing returns to scale. So in this case, you're doubling labor, doubling capital, you're doubling the amount you produce. In this case, you're doubling labor and doubling capital, but you're multiplying what you produce from 100 to 300, so you're getting 3 times as much output from twice as much in inputs. And in this case, you double labor and capital, you only get 50% more. Now, when people estimate production functions empirically, and you can think of a lot of reasons why you might want to do this. Well, certainly if you're going to try to maximize profits, you want to know how changing your scale of production is going to affect your costs. So you'd want to know the production function for that purpose. And so how do you investigate this? Well, to some extent you may have inside knowledge. Well, you'll start, if you're in a position to make these decisions, you almost surely do have at least some inside knowledge about the engineering processes, and you might be able to kind of deduce from that what it will be, but that doesn't always work that well. Another way is you could try to estimate them empirically, and this Cobb-Douglas production function, Q equals A, K to the A, L to the B. This is just a sort of a standard basic form of production function, and I mean, I don't know if it fits many production processes perfectly, but it might be a somewhat reasonable description of many production processes, kind of approximate. If you wanted to estimate it, then again, for one thing, you have to have a lot of data about capital and labor, and they have to have varied somewhat over time in ways that allow you to estimate this, and there have to have not been whatever technological changes or other stuff going on that would distort the result, but if you do have a data series with capital, labor, and quantity, you could run this regression. Notice that when it's in this form, you can't really run a regression because it's not linear. Regressions have to deal with linear relationships. If you think that these are sort of products of each other, that they're related in this way, and there's a good reason to think that. I mean, capital makes labor more productive. Labor makes capital more productive. So they're not just added to each other. They're multiplied by each other. And so you do want the production function to be in this form. This is much more realistic than one that just added capital and labor. But if you take logs of this, then you can turn it into something linear, and then that could be estimated. Okay, this is basically a slide of kind of buzzwords that you might hear in management, so I want to try to give you an idea of what they mean. Product innovation. This is you're coming up with some new product. What you're selling to the customer, what you're selling to your client is something new that either they haven't seen before, or at least they haven't seen it from you. Maybe you're modifying, improving the quality of a product, but in any case, it's on the product and it's what you're selling. Process innovation. This is where maybe you're selling the same thing, but you've found a new way to make it. You found a new, faster, cheaper way to make it. So that's process innovation. Product cycle model. This is the idea that many products, they kind of go through a cycle where initially there's something that's innovative and new, and the cutting edge firms that develop them are the only ones who know how to make them. And then as time goes on, then maybe patents expire. That could be one thing, but it might also just be other firms figure out how to do it. And then the issue becomes not selling and marketing this. I mean, another factor is customers get used to it. Customers start to expect the product to be provided, and then lots of firms can jump in and basically mimic what the leaders do. It may be that the leaders who came up with it are not the ones who are best at producing it cheaply, or aren't interested in trying to produce it cheaply. They might move on to something else. So this is the idea of the product cycle model, where new product comes in, then it becomes generic and spreads to other firms. Just-in-time production system. This is something that the Japanese kind of pioneered, and then that was quite successful there back in the 70s, so it got imitated in many other parts of the world. This is the idea that you've got a production system where the parts that you need, they arrive just in time to be put into your production process. What are the advantages of it? Well, you've got a lot of stuff. You don't have a lot of stuff now sitting around on the shelves waiting to be processed. So you can save money on warehousing, maybe on logistics. Although I think a lot of times firms actually end up spending more on logistics for this because you save on the capital costs of the components in process. So I mean, if it takes you a year to get a car to a buyer, well, through that year you don't have the money, and you could have been earning interest on the money. So that's another factor. Probably even more important, it's just fashions change, being able to respond to fashions quickly, being able to introduce innovations quickly. If you have a big backlog of components which are supposed to go into the production process, and then you say, oh, well, we've got a new design. Well, what are you going to do with all the components for the old design? Maybe you can just keep producing the old design for a while, but by that time your new design might be stale. Or maybe you can just throw away all the components for the old design, but then you've wasted all those components. So just-in-time production means if you bring a new product online, you can start delivering it faster and without wasting a lot of production from the previous product. Competitive benchmarking, this is basically where executives from one firm go and look at how another firm operates to try to figure out, and it's actually, I think this is usually done with the consent of the firm, so I'm not sure exactly all the motives that are involved there, but and then computer-aided design and computer-aided manufacturing. So computers have become useful in developing new products and then even in producing them as well. Okay. Yeah, actually, I don't remember why this is in here. It might be an example, though, of... so G decides smaller is better. You notice here, GE has $123.1 billion worth of sales, 756,000 employees. They don't see... Sales per employee, I mean, they have the largest sales relative to the other two. But their sales per employee don't look very good. Ford has a smaller scale of operation, about half the employees, much more sales per employee, and then Chrysler's worse than Ford, but also better than GM. Yeah, this isn't exactly a clear story of what's going on. I mean, it's just three companies. Maybe Ford just happens to be well managed, but it does at least suggest that maybe GM is not doing well by operating on such a large scale. That there's actually some diseconomies of scale at this point, and they'd have a good idea. It would be a good idea for them to downsize. Okay, so output elasticities. We talked about these before. So this is where you say if you increase your output by a certain amount, if you increase one of the inputs by a certain amount, how much do you increase the output? So if you go back, by the way, to the Cobb-Douglas function, production function, in this case, the output elasticity of capital is A. Output elasticity of labor is B. It's maybe a little bit tricky to demonstrate why that is, but so if you increase your capital, then it will, for each 1% increase in capital, there will be a 1% times a percent increase in Q. So if A is 0.3, there would be a 0.3% increase in quantity. So somebody's gone through and empirically estimated these output elasticities for a whole bunch of industries. And of course, this is challenging to do because you know there's all sorts of things you have to worry about and control for and so on. But furniture, chemicals, so capital there's interesting variation here. I mean, 0.2, 0.2, 0.4, 0.5. Let's see, what's the highest one? Maybe that's the highest one. No, stone and clay. So here there's lots of elasticity with production workers. Here it looks almost like it doesn't even matter that much. You increase your production workers a little bit, it doesn't really make that much difference. I mean, I don't know if I exactly believe that, but it's non-production workers in this case seem to be more important. Usually non-production workers seem to be the least, but yeah, it varies a lot across industries. Rubber and plastics, non-production workers are getting in the way, so the fewer you have, the more you produce. So anyway, somebody's trying to apply this and trying to figure out in different industries how capital and labor contribute to the production process. Okay. Acquiring new technology. So this is broken down into product innovation and process innovation and product innovation. Independent R&D, and it doesn't give, I don't remember what the data is on these firms, but they've got rank order, and it's probably based on some kind of a survey. So 1, 2, 3, 4, 5, 6, 7. Independent R&D is 1. Licensing, public working down, conversations with employees of innovating firms, patent disclosures, reverse engineering. For product innovation, the main difference is reverse engineering is a little bit higher. And I guess hiring employees of an innovating firm, a little bit higher. Fairly similar order, but so these are various methods firms can use to improve their technology. Very good.